Good afternoon and welcome to NASA's Kennedy Space Center in Florida. We're here for the mission science briefing as part of NASA's Cyclone Global Navigation Satellite System mission, otherwise known as CYGNSS. I'm Sean Potter from NASA's Office of Communication. I'd like to welcome everybody here today. With me are three scientists who are working on this mission, all from the University of Michigan's Department of Climate and Space Sciences and Engineering at the University of Michigan in Ann Arbor. And I'm going to introduce them to you, and then they've got some opening remarks, and we'll take some questions after that. So immediately to my left is Dr. Chris Ruff. He is the principal investigator of the CYGNSS mission. Next to him is Aaron Ridley. He is the CYGNSS Constellation scientist. And immediately to his left, we have Mary Morris, who is a PhD student working with Dr. Ruff on applications from CYGNSS data, and they all have some exciting information to share with you about how this mission will work and some of the incredible science that it promises to bring us and the hurricane forecast community. So we'll start things off with Chris Ruff. Chris.
Thanks, Sean. So I wanted to start by giving a little bit of background to sort of set the stage for what CYGNSS is doing and why it's doing it. So CYGNSS is designed to measure the winds over the ocean in hurricanes, and I wanted to first give you examples of how we measure winds from space over the ocean today, and then how we measure winds in hurricanes today. So if I could have the first slide. Yeah, so here's an example of how we measure winds over the ocean from space today. This is the NASA TRMM satellite on the left, and then some of its data products on the right. The top image on the right is the precipitation data product, the rain rate, and the one on the bottom is the wind over the ocean. So TRMM can measure wind over the ocean, as can CYGNSS. There's two important characteristics of these data that point to current limitations that we're planning to overcome with CYGNSS. The first one is if you look at the places in the top image where there's heavy rain, particularly near the equator in the ITCZ, if you look at the same spot in the lower image measuring the wind, you'll see that the winds are black there. And the reason for that is this satellite, as every other satellite up there now, cannot measure wind through heavy rain. That's a fundamental limitation with these types of measurements, and the reason for that is the wavelengths that they operate at. TRMM operates at an 8 millimeter wavelength, and raindrops are typically 1 to 5 millimeters in heavy rain, and if the raindrops are comparable in size to the wavelength of the electromagnetic waves, you get a lot of scattering, a lot of absorption, and you can't penetrate through. So we just can't measure wind under heavy rain from space. That's one limitation. The other one, if you look at the captions to these two images, you'll see these are 3-day data products, and what that means is the satellite orbit takes 3 days to come back around the same place. So it takes 3 days to make a complete measurement of the entire Earth. And this is fine for a lot of applications, but for extreme weather situations like hurricanes where things change on the time scale of hours to maybe a day, if you make a new measurement once every 3 days, it's very likely that you'll miss important parts of the evolution of the storm. So those are the two things that we're trying to overcome with CYGNSS, measurement through rain and measurement more often in hours instead of days. If we go to the next slide, here's an example of how we can measure winds today in hurricanes. This is an instrument called the SFMR in the lower left there, and it's installed on the NOAA P3 Hurricane Hunter airplane. So these are airplanes that fly directly into storms, into hurricanes, and they can make measurements of the ocean surface in heavy precip, in particular in hurricanes. And the way they do this is they operate at a much longer wavelength. SFMR operates at about a 5 centimeter wavelength, which is about 10 times the size of a raindrop. And in this case, there's some interaction with the rain, but not total attenuation. So you get some interaction with the rain, and you get some interaction with the surface, and by analyzing the data properly, you can correct for the rain attenuation and measure the wind. If we go to the next slide, this is an example of a data product measured by the NOAA P3 Hurricane Hunter when it made an overpass of Hurricane Katrina about a day before landfall. So there's an image in the top left of Katrina, and if you look closely, you can see a black arrow through the eye. That's the flight line of the airplane. And then in the lower right is the data that was measured, or the retrievals that were estimated from the data during that overpass. And you can see both the the rain rate that's retrieved as a secondary parameter to correct for its interaction, and then the primary measurement of the wind speed itself. You can see the maximum winds occurring on the eye wall where the rain is heaviest, and then there's calm winds in the eye of the storm. So it's important to note here that these measurements are made directly under the airplane only, and you need to fly an airplane out there to make these measurements. So what we're trying to do with Cygnus is combine the global coverage that you get from a satellite with the ability to penetrate through the rain that you get with one of these Hurricane Hunter instruments, and also improve upon the sampling characteristics of the large weather satellites that take 3 days to revisit. And the way to do that is to operate at long enough wavelengths to penetrate through the rain, and in order to improve the sampling more often than every few days, we need a lot of satellites. And the way to do that in a cost-cap mission is to make things cheaper so that you can afford to build a lot of satellites. And that leads me to the next slide, which illustrates the way we make these measurements. So as you heard in the engineering briefing earlier, Cygnus is basically the receive half of a radar, and the transmit half of the radar is the GPS constellation of navigation satellites. So there's 30 GPS satellites up there now, and they're constantly transmitting their signals down to the Earth for navigation purposes. They're intentionally designed to operate at a very long wavelength, 19 centimeters, in order to be able to have navigation work when it's raining heavy. Like, for example, when you're driving in your car, your navigation system works just fine when there's heavy rain because it operates at such a long wavelength. So the GPS transmitters are there, or the signals are there all the time, and what we've done with Cygnus is we've taken a commercial navigation receiver and essentially hacked into it and modified its processor so that it does both navigation, and it also measures the distortion of the navigation signal after it reflects off of the ocean surface. And by looking carefully at the nature of the distortion, we can back out the properties of the ocean surface that are forced by the local winds. And I've got a series of slides here to illustrate the interaction between the electromagnetic signals and the ocean surface to show how it is that we measure wind. So if we can go to the next slide. So here's an example of specular scattering in optical wavelengths. So you can see the moon above the horizon, and then you can see a reflection of the moon in the lake. And the water, the lake surface is very calm, there's no wind blowing, and because of that, the reflection of the moon is almost as sharp as the moon itself. And this is called specular reflection in electromagnetic terminology, and what that means is mirror-like reflection, where the surface does not distort the reflection. And if the ocean were perfectly smooth, the GPS signal would reflect off of the ocean and be received by Cygnus, and it would still look like a regular navigation signal if there was a nice, smooth, mirror-like specular reflection. If we go to the next slide, you'll see what happens when the wind blows. When the wind blows, there's friction at the water surface, and that roughens the surface, and this is called diffuse scattering rather than specular scattering. So here's an example, again, in the optical wavelengths where the moon is reflecting off of a roughened surface, and you can see that the reflection is not a nice, sharp picture of the moon, but now it's a diffuse version. And this happens in optical wavelengths like this, and it happens at radio wave wavelengths like GPS as well. And if we go to the next slide, you'll see an example of this. So this is the first measurements of GPS scattering off the ocean measured from space. It was measured about 10 years ago by a technology demonstration mission that was flown with a prototype of the Cygnus receiver. This is when it was first, like the details were first worked out about how to hack into a regular navigation receiver to do these type of reflected measurements. And this is a GPS 19 centimeter signal scattering off the ocean surface, and you can see that the specular part of it, of the reflection, is that bright red part at the top, and then the yellow kind of horseshoe-shaped part is the diffuse scattering away from the specular point due to the roughening of the ocean surface. And in general, the rougher the surface is due to increased wind speed, the more diffuse scattering there is, the less specular scattering there is, and Cygnus makes measurements just like this every second, and from that we can derive the wind speed. Okay, if we go to the next thing to play, I think, is a video. This shows you how the sampling works with Cygnus. So there's 8 satellites in a single orbit plane. Each satellite has antennas pointing towards the surface, looking at the scattered signals. And those blue ellipses, those are the locations of the specular points from the GPS transmitters, and as soon as they enter the antenna beam that's looking down at the ground, that's those red ovals, the onboard processor latches onto them and begins processing and generating those images of the diffuse scattering. There's enough processing horsepower on board to measure 4 of these specular points at a time. So it's always tracking where the specular points are, and it takes the best 4 in the antenna pattern and processes them into winds. So essentially, we're measuring winds along these blue lines as the satellite orbits along. And you can think of this kind of like there being individual airplanes, kind of virtual airplanes, P3 airplanes, somewhere in the tropics, and underneath of them they're making winds, making measurements of the winds, and with 8 satellites and each satellite able to make 4 measurements of the wind, it's kind of like having 32 virtual P3 airplanes someplace in the tropics making winds at all times. And if you take all of those winds, aggregate them together, you get the data product that Cygnus generates. With 8 satellites, there's about 7 hours between measurements at any given spot in the tropics on average. So we're able to make measurements much more often than that 3-day refresh rate of the TRMM satellite. And I think I have one last slide here. This is an example from we have a detailed software simulator of the mission and of the interactions of the GPS signals with the ocean surface, and this is an example of the type of product that we're expecting. This is a simulated tropical cyclone in the left, and then a transect of the specular point passing through the eyewall of the satellite, that black line, and that plays the same role as the flight line of the airplane in this case. And then on the right, we have an example of the true wind in our simulator, and then the retrieved wind, including all the realistic sources of errors and calibration and noise and so on that we're expecting. And you can see that it picks up the calm water in the eye of the hurricane, and then the strongest wind in the eye wall as it penetrates through the maximum wind. So that's the data product that we're expecting. And I guess I want to say just one other thing about the nature of the satellites and how we're able to do these measurements. It's really critical that we have many of these satellites in order to get the sampling down to every 7 hours. And the way to do that is to make the individual satellites cheap. So the GPS receivers themselves are very low power and very efficient because they've been optimized by commercial industry for commercial navigation, and that makes the satellites be nice and small and cheap. And the other thing that's really critical about this is the actual satellite itself has to be simple in order to keep the price down. And one of the key things that keeps it simple is the fact that it has no propulsion. So once these satellites are launched, they're initially very close together, and then they start spreading apart, and we need some way to get them evenly spaced out around the orbit without propulsion. And the way we do that is this clever trick that Professor Ridley next to me figured out, and I'll let him kind of tell his tale.
Great. Thank you very much. So as Chris just talked about, when the satellites are launched, they come off of the Pegasus satellite, or Pegasus rocket. If we really wanted to, it would be great to have 8 rockets actually launching every single one of these, but it would be extremely expensive. And so the best method is to have them up there, take them up on one single rocket. And as Chris just talked about, I'm going to use some props here. When they come off of the rocket, they're basically going to be together. All right, they're going to be spreading apart very slowly from each other. They're going to be orbiting around the Earth at about 17,000 miles an hour, but with respect to each other, they're going to be moving only at about 2 miles an hour. So they're going to move apart from each other very, very slowly. And after about 3 months, they will basically, one will have lapped another one, and it will come around like this and fly over the other one. And we don't really want that to happen. What we want to happen is for them to basically stay at about the same distance apart and fly in tandem with each other. We want them to be spaced about 3,000 kilometers apart from each other, 3,000 miles apart from each other. And the way that we're going to do that is that as these things come apart from each other, then we're going to start tilting them up. And this one will go into what's called high drag mode. All right, so what happens is that up it at about 500 kilometers altitude, there's still a lot of air up there. And all satellites, it's the second largest force that the satellites feel besides gravity. They feel aerodynamic drag. And so just like a biker would tuck down and feel less drag force, these satellites are flying like this and don't feel very much drag force. But when you tilt it up, they feel a lot of drag. And so as this one is going faster than this other one, you tilt it up and you slow it down with respect to the other one. Okay, and so what we're going to do is we're going to have meetings every week where we'll decide which satellite we want to put into high drag mode. I was supposed to show some pictures that illustrate this a little bit. So if you show the first picture, or the first video, this is the deployment sequence. So all the satellites are on one rocket. They're all bunched together, and they all pop off. And they're moving about 2 or 3 miles an hour away from each other. And it will take them about 3 to 6 months to basically overlap each other, to start lapping each other. You don't want them to lap each other because if one is above the other one, they're measuring exactly the same thing on the Earth. And we don't want that to happen. So we want them to be spaced apart from each other. So if you show the next slide. Now, the satellites are going to orbit at 35 degrees inclination. The reason we chose 35-degree inclination is because that's where most tropical cyclones happen. So this plot shows tracks for tropical cyclones for about 10 years. And you can see the vast majority of them are within this white zone, which is between plus and minus 35 degrees. We don't want to do something like a polar orbit because there are no tropical cyclones up near the poles. We want to stick where the tropical cyclones are. And so we planned the inclination to be 35 degrees. We'll go between plus and minus 35. We have figured out how to space these satellites out so they're equally spaced around the orbit. And then if you go to the next movie, it shows how the coverage happens of all these specular points. Chris showed just one small time slice, but this shows 24 hours of Cygnus measurements. And you can see that we cover the entire globe in about 24 hours. We actually measure multiple times over the same place fairly often with this. And you can see, if you look very, very closely, we have about 80 to 85% of the spots in the plus and minus 35 degree latitude band covered by Cygnus every single day. And that's all I have.
Great. Now we'll turn it over to Mary Morris to talk a little bit about some of the applications of the Cygnus science.
Thanks, Sean. So now that we've heard a little bit about the science and the engineering aspects of Cygnus, I'm going to talk to you all about a tool that we've been developing for the science applications. Why should you care about Cygnus? So at the University of Michigan, we've been developing this tool called SIFT, or the Storm Intersection Forecast Tool. And the reason that we developed SIFT is because we needed a way to predict ahead of time when we're going to get valuable storm data. And then after we answer that question, we want to know how soon after we get that data can we then downlink it to the ground and get it to the user community as soon as possible. So what we're going to do today is we're going to do a little experiment. We're going to pretend that Cygnus launched a year ago, and we're going to see what we would have seen during Hurricane Matthew a little over a couple of months ago if Cygnus had already been orbiting. So let's go to the video clip and see this tool in action. So what you're seeing now is SIFT in sort of a global view mode. Each of these colored triangles represents one of the Cygnus satellites, and the dots that surround each satellite are the specular points. That's where our data are going to be. That's where we're able to measure ocean surface wind speed. What I just turned on are these circles around our ground stations in Hawaii, Chile, and Australia. So when our orbit propagator predicts that these satellites are going to be moving over these ground contact zones, that's where we're going to be able to downlink our data. What I just turned on is one ground track for one satellite over about an orbit, just to give you guys, and again, additional ideas of what the sampling properties of Cygnus are going to be. The next thing that we're going to ask of this tool to do is to tell us where our data are expected to be over this time period. So I'm about to turn on the specular points for the same time period. So each of these colored lines represents one of the different satellites. And you can imagine that if we added time, all of these satellites in combination give us great coverage over the tropics where we expect most of the tropical cyclones to be. The next aspect of this tool is to determine when Cygnus is going to intersect Hurricane Matthew. So what I just turned on is this red bright circle, and that's the current position and size of Hurricane Matthew according to the National Hurricane Center's forecast. Hurricane Matthew for this time period is forecasted to move to the west and then eventually turn to the north. The future locations are shown by the lighter red colors. So we're using this tool to propagate the orbit forward so that we can see where Cygnus is going and where the hurricane is forecasted to go. Right now we're getting pretty close, but Hurricane Matthew is running away from us a little bit here. But we're starting to get close, and we're going to zoom in really, get a zoomed in view pretty soon, just to see what our data looks like here. So I'm going to turn on all of the specular points for a couple of hours around this time point, now that we know the sort of general gist of the time period that we're looking at. So all those lines are the data. Right now you're seeing the satellites propagate on the bottom right-hand portion of the tool. And right now we're getting crossovers through that bright red circle. That's the current position and size of the storm. All of that data in that bright red circle is stuff that can be used to answer questions like, how intense is the storm? How far out do strong winds extend? What is the destructive potential of the storm at the time? And that's really valuable data. So let's zoom out and let's look at all the data collected over this same time period. In addition to all of the Hurricane Matthew data that we're getting data in the environment of Hurricane Matthew as well as global data. The next thing that we want to ask of this tool is how soon after we get that really valuable data can we then downlink it to the ground as soon as possible. So let's go back to our ground contact zone view and put the satellites back into motion. And you're going to see that right after we go over Hurricane Matthew's area, we go straight towards the Australian ground station where we can get the data down to the ground within an hour. And that's a really great data latency for all of our science applications. So that's all I have for today. I just wanted to end by saying this is just one of the many amazing projects that I've been able to work on as a student on the Cygnus team, and I'm really excited to see what Cygnus does in the future, and I hope you guys all stay tuned. Thanks.
Great. Thank you so much, Mary. And as I mentioned at the beginning of today's briefing, you are a PhD candidate at the University of Michigan working under Dr. Ruff. And as I understand it, you're actually preparing to defend your doctoral dissertation later this month?
Right. December 20th is the date.
And you're actually using the Cygnus project as the basis of your research, correct?
Yep.
Great. Well, good luck with that. So.
Thanks.
All right. So now we have some time to take some questions from folks both here in the audience as well as on the phone and via social media. And we'll start with questions here in the audience, and then if there are any on the phone, and then social media. And just a quick reminder for people who may be asking questions via social media that you can do so by using the hashtag AskNASA. But we'll start with some questions here in the room. We'll start right here in the front row, red shirt. And if you could identify yourself and then ask the question.
Sure.
Thank you.
Bill Jellin with Wheat Report Space. So for Mary, when the first one goes over Matthew and then we get the information an hour later, we're now waiting until the satellites come back over Matthew. So just what's the guess from one measurement until it comes back around and is able to intersect Matthew again in your video? How long is that?
So on average, it's about 7 hours, but it depends on the case and how the hurricane is moving in addition to the satellites. But in general, I've found that when we, hit the hurricane, when we intersect it, we hit it really well. We're never just gonna like barely graze it or, miss it, by just a little bit. So I'm really excited about all of the applications.
Okay, another question. How about right behind the gentleman who just
Rick Lansby with WFIT. I guess I'm a little confused about the 7 hours. Dr. Ruff, does that mean if I'm standing in one spot, a satellite would pass over me every 7 hours?
That's exactly what it means. So the sampling for this type of technique, there's a fundamental difference between it and a typical imager, polar orbiting wide swath imager that typically has an exact repeat orbit, and there's an exact time that it comes back around any given spot. That's the revisit time. That's sort of the standard approach to temporal sampling with low Earth orbiting satellites. With Cygnus, our orbits and the orbits of the GPS satellites are completely asynchronous. So the location of the sample and the time of the sample, it's determined by the relative locations of those two satellites. The specular point on the ground is formed by exactly where those two satellites are at any given time. Because the orbits are asynchronous, the locations of the samples move around all over the place, and they're not really deterministic. The right way to analyze it is to treat the sampling properties as a statistical property, a random process, and then calculate probability distributions and statistics of samples. That's a clean mathematical way to handle the sampling properties. So there's a statistical distribution of how often you'll come back to the same place, and the average of that statistic is 7 hours.
All right, I think we had a question here on the other side in the front row.
Jim Siegel, I'm with Celebration News and Spaceflight Insider. Also, I'm a graduate of the University of Michigan, so go blue.
It's a nice hat.
I'm interested in how I can explain to my readers what the advantage or the outcome of having this in space is for them in non-technical terms. Say somebody from Michigan State. How would I describe that? How would I describe what does this do that they're not going to get today from the weather forecasters?
Do you want me to answer? I mean, you're much better, but I could try.
Yeah. So if you look at the general characteristics of hurricane forecasts today and over the last couple of decades, hurricane forecasts of the location of the storm, the storm track forecast, have been steadily improving over the decades. And the forecast of the intensity, which is the maximum sustained wind, have not improved anywhere near as much as the forecast of the location. So being able to predict where a storm is going to make landfall has gotten steadily better, and being able to predict how strong it's going to be when it does make landfall has not improved anywhere near as much. And the general consensus on why that is, which has been backed up by a lot of simulation study, computer simulation studies, is because of our inability to measure what's going on in the middle of the storm. And that's what the focus of the types of differences between Cygnus and previous satellites. That was what we really focused on, was trying to address that need. So what we're hoping in the end will happen with this data, and we've done a lot of simulations that tell us that this should happen, is that our ability to forecast how strong the hurricane is going to be when it makes landfall will get much better. Yep.
All right. I think we had another question next to that gentleman.
Jason Ryan, also at spaceflightinsider.com. I'm not sure who to field this to, but I hope you can help me out. Now, you mentioned the lack of a thrusters or propulsion system on the spacecraft that helped reduce costs. Can you give us a couple other examples of ways that costs were cut for this particular mission? Thank you.
Well, one of the things is the number of spacecraft. So in theory, we could have flown more spacecraft. The Pegasus rocket would have allowed us to fly maybe 1 or 2 more spacecraft. But as you have more mass, you come closer and closer to the limits of the rocket. You also come closer and closer to the limits of your budget. And so we made some hard decisions when we were doing the mission planning to figure out exactly how many spacecraft would be the optimal number of spacecraft for the cost, for the mass, and for the science return. You would like to have as many satellites as physically possible up there, but you have to live within the realism of the mass constraints and the dollar constraints. And so that was a big trade-off that we made.
I can give you one other example of a trade-off. When you design satellite architectures, there's often a desire to make them as reliable as possible, and the way you do that is by having redundant systems. You have the same thing in the satellite more than once, so that if one of them breaks, you can switch to the other one. And if you don't do that, then you have things called single-string failures, where if that fails, you're dead. Okay? And with the Cygnus satellite, there's very, very few parts that are redundant, just a couple. And most of it is single string. And the reason for that is we have 8 satellites. We need 6 to meet our science requirements. And so we have redundancy at the constellation level, but the individual satellites are not redundant hardly at all. And it made them much easier to make, to build. And because of that, we could afford more of them. So we've moved the redundancy to the constellation, and that had a big impact. Yep.
Okay, I think we've got one more on this side, and then we'll see. We've got some more on the other side of the room.
Hi, Ken Kramer, Universe Today, Northeast Astronomy Forum. Kind of to follow up on this, if you had the budget and you could launch, let's say, a second series of 8 satellites, could you maneuver them to get the data back like every 3 hours or so? And would that be useful?
Go ahead.
So with the orbit plane that we have right now, you have just one orbit around the Earth. If you actually had two satellites or two planes, then you could have an orbit plane here and an orbit plane there. And so it would cut our revisit time, like Chris was saying, from 7 hours down to, say, 3 hours. And so you could basically have data every 3 hours of the hurricane. And so it would give you much more value in that.
All right, how about over on this side of the room? We have any questions? One right there in the second row.
Bill Harwood, CBS. I want to visualize. I know they're all in the same plane, but how spread out is it when everything's all lined up where you want it? I mean, you're controlling altitude, right, with drag.
Yes.
But how far apart are they crossways or normal to the orbit plane, if you will?
That's a good question. So they're basically in exactly the same orbit plane. So when the rocket kicks them off, two will be kicked off. One will be kicked off forward, and one will be kicked off backwards, and they're in the same orbit plane as the rocket. And then two will be kicked off almost perpendicular to the orbit plane, but the velocity along the orbit plane is 17,000 miles an hour, and the velocity perpendicular is 2 miles an hour. And so it makes a very small change in the inclination, not enough that you'll ever notice it really at all.
Okay, other questions here in the room? We've got some more on this side.
Thank you, James Dean, Florida. Dr. Ruff, you just been discussing the affordability of these satellites. So I just wanted to ask, what is the value of each spacecraft, and does that? I mean, I see what's listed as NASA's investment in this mission. Is it that divided by 8? What other investment
Value-
also
you're talking
is there in
about
the
dollar
mission?
value,
Yeah,
not
yeah. How
value
much do they
in
cost?
Loss of life or something. The dollar value. I don't know exactly what the recurring cost is. I mean, just in general, it costs 10 or more times more to build the first one than the next 7 because of all the design work, if you really break it up that way. And I don't know what the recurring cost is. I should find out in case NASA wants me to build a bunch more of them, I guess. It's certainly much less than 1/8 of the total mission cost, because the recurring cost happens just once, or the non-recurring engineering work happens once.
Okay, let's go to one right behind him, and then I think we have one on the phone.
Hi, Stephen Clark from Spaceflight Now. A couple of questions. One, just to clarify, the 3 ground stations that were mentioned in the animation, are those the only 3 that are being used in the mission? And also, what are the plans, or are there any plans to operationalize this data if the demonstration works as you expect? Are you in contact with anyone from the Hurricane Center or the National Weather Service, or is that something that would need a follow-on mission to operationalize? Thanks.
Yeah, okay, I'll take that one. So the first question was how many. Yeah, those are the only 3 ground stations we have. We've contracted with a private ground station vendor, USN, and those are the 3 stations that we've contracted to use. So those are sort of fixed. And then the Cygnus mission, it's a kind of research and discovery mission, not an operational mission, and it's a NASA mission, not a NOAA mission. That being said, there's a number of NOAA investigators on the Cygnus science team, and there are a number of people at the National Hurricane Center that are involved in Cygnus. They know all about what we're doing. I've gone down there a number of times and briefed them, and they're very excited at looking at the data. They're very they're careful and cautious about using new data types, and there's a careful vetting process that they go through over a period of years when they look at the quality or potential impact of the new data sets on their forecast skill. And the intent is to do that over the first couple of years of the mission, and then they're going to decide what to do next. But they very carefully test out the impact of new data sets on their forecast skill before they start to use them.
Okay, we'll go to a question on the phone, and just a reminder to please identify yourself and your affiliation.
Hi, this is Michael Phillips with weatherboy.com. With the data that you're collecting, can you talk about how that data will actually be validated and verified? Are you looking at data from sources like the National Hurricane Center to verify the information you're collecting is accurate?
Yeah, so we're working with the what are they called? AOC, the part of NOAA in Miami that flies those Hurricane Hunter airplanes. They know what we're doing, and we actually went through a whole training process this past hurricane season using that tool that Mary showed you, the SIFT tool, where we would forecast where we would have made overpasses of hurricanes like Matthew and a couple of the others this year, where we would have made overpasses and when, 2 or 3 days in the future, and also what our heading would be. And we talked to the people there that were flying the P3s, the navigators on board, about what we were doing, and we worked out a procedure to tell them what we would like, and they're very interested in this, and they want to help, and they're willing to try as much as possible within the constraints of their charter to underfly us when we go over hurricanes and to fly the flight line of the airplane parallel to our ground track, our specular point transects, so that we have as much matchup as, or coincident matchup as possible between the airborne measurements of the traditional way of measuring the winds and the Cygnus measurements. So that's going to be our primary validation tool in the hurricanes themselves. And then away from the hurricanes, there's a lot of standard ways to validate the quality of wind retrievals, and we'll be using those as well.
Great, thank you. I've got another question from a caller on the phone. This one from Jesse at space.com.
You guys can hear this? Yeah? Good. All right. I was just wondering, the mission time, the total, it's going to be a 2-year mission and then maybe an extended one after that. And I was just curious if you were funded for the whole 2 years.
Yeah, we're gonna turn on the science mode about sometime during the second month after launch, and the intent is to stay on in science mode 24/7, 100% of the time, 100% duty cycle for the rest of the mission. So we'll be making measurements over hurricanes, but they don't happen that much statistically. The other 99% of the time we'll be making measurements over the ocean. We also make measurements over land, for that matter, which has other science applications. But yeah, we'll be running all the time over those 2 years.
Okay, great. Do we have any other questions here in the room, audience? If not, do we have any on social media? I believe we do. So Sarah?
All right, so I've got 2 questions from social media here for you. The first is, when do you expect the data to start being sent back to Earth?
Well, if by data you mean the engineering communication with the satellites to make sure they're healthy, that happens the first day. Within about 2 hours and 45 minutes is when we are hoping or expecting to start getting communications. I think our first light science data is going to happen the second week, just to make sure that it works from an engineering functional performance perspective. And then sometime during the second month, we'll be switching into regular science mode and just running in science mode.
Okay, and our next question and final question from social media is, will Cygnus help inform us about weather and or climate outside of hurricane season?
I'm going to let Mary answer because, well, she's got her dissertation defense in a couple of weeks, and I figured this is a good chance for me to throw a bunch of science questions at her to get her warmed up for it.
So the answer is yes. There's a lot of different science applications that a lot of the members of the science team are actually already working on. So we have an entire section of our science team that's working on increasing our understanding of tropical convection, the MJO in particular, and even stuff over land like soil moisture and other processes that we're interested in looking into, seeing what the data tell us.
Wonderful. Do we have any other follow-up questions here in the room? We got one here in front row.
Jim Siegel from Spaceflight Insider again. Just to follow up from my question earlier, having this Cygnus system in space, is this going to either replace some of the Hurricane Hunter airplanes that are out there now, or is it better than what they collect now? Can you give us a sense of how this compares in terms of the value of this information and the accuracy versus what we have today from whatever source?
Right. So I think they're very complementary. They're not. It's not going to ever replace those Hurricane Hunter planes for several reasons. One is the spatial resolution of the Hurricane Hunter measurements is much better, about 5 kilometers, and we're about 20 kilometers. So you get a finer resolved variation in the wind gradients as you pass through the eyewall. But the temporal sampling characteristics for Cygnus are much better because we have global coverage with lots of satellites. Another important difference is that, you know, the hurricane hunters have these, that SFMR sensor measuring the wind at the surface, but they have a lot of other sensors as well. And in particular, they're able to measure the vertical profiles of the temperature and the wind and the air pressure with dropsondes. And the vertical structure is you know, of fundamental importance for understanding the physical processes in a hurricane, and also for understanding aiding in the prediction software, the forecasting software. So measuring vertical profiles is hard in general from satellites, and in heavy precip, there's really no good way to do it now. So we don't know how to replace those airplanes now, given the sort of state-of-the-art of remote sensing capabilities from space.
All right, I think that's all the time we have for today. And just as a reminder, this mission is scheduled to launch Monday morning, and you can watch it live on nasa.gov. And you can find out much more about this mission by going to the special mission website at nasa.gov/Cygnus. Thank you very much for joining us.